Hello again. Let's talk about a thing called differentials and the local, just the linear approximation or the tangent line approximation. Suppose that f is differentiable on the open interval ab and that c and p are points inside the open interval. They're going to be x values or domain values. Suppose that f of c is easy to find by hand, but f of p is not. We can use the following approximation called the tangent line approximation or linear approximation, just whichever one you'd rather call it, to find f of p. Now here's how we define that approximation. And guys, I'm not going to go into why this works well. Just trust me that it does, as long as p is very close to c. Now I also need to suppose that p and c are very close. Or I'll just say close. Okay. Now, if P and you can still try to use it if P and C aren't close, but you're not guaranteed that it'll work very well. Okay. And even if P and C are close, you're not necessarily guaranteed. But as long as a function is not too weird, there's a fairly decent shot that this will work nicely. This is just an approximation, and when I say close, I've not rigorously defined that at all. Just use your common sense notion of close. I don't want to go into analysis. Okay, but if f of p is hard to find and your professor is just not going to let you use a calculator, what you can do is find f of c, which is easy to find, and then plus f prime of c, p minus c. And I'm assuming also, and we're assuming f prime will also be a pretty easy thing to find. F of c is very easy to find. F prime of c is fairly easy or very easy to find. Now, and of course it's trivial. P minus c is trivial, and you can just p minus c. You'll do that by hand. Like if let's just say c, it could be 2. P may be 1.99. Now p, f of 1.99 may be hard, but f of 2 may be pretty simple. And f prime of 2, you'd have to do the derivative first and then plug 2 into it afterwards. That's what this notation means. But that still may be a fairly easy thing to do. And of course, 1.99 minus 2 would be negative 0.01, and that's negative 1 over 100 or whatever. So you'd multiply f prime of c by negative 0.01. You can do that by hand. Get this, and separately get this, and add the 2. We'd probably already have this, and then separately get this, and then add the 2, and I'll show you how it works. And you know what? Oops, I forgot. That's not exactly equals. And by the way, guys, these swervy equals, now this is exact, but this is not. These two, this here and this here, these are swervy equal. That means that means approximately equal to. If you see swervy equal signs, that means approximately equal to. It doesn't mean exactly equal to. Now this right here does. This is exact. This is approximate right here. And so is this. Okay, now here's the deal. Sometimes we get lazy, and instead of writing f prime of c, p minus c, we prefer to call it dy. And sometimes even if we don't want to altogether write this as dy, now dy is f prime of c and times p minus c, but we go ahead and I'm going to be lazy in the middle. Dy is f prime of c, p minus c, and I'll insert that in here just to avoid confusion. But guys, we're going to let p minus c be called something called dx. So we're going to let dx equal p minus c, so we can replace p minus c with dx, and we're going to replace f prime of c dx, which is f prime of c p minus c, with just altogether dy. So dy equals f prime c p minus c, and I say as much right here. Yeah, okay. And we call dx and dy, they're referred to as differentials. So let's scroll down here. Let me go down. Now consider, this would be a hard guy to do by hand. 64.12 raised to the power of 2/3. Now here's the function that's begging to be called upon is x to the 2/3, right? Because our number's been raised to the 2/3. We're going to replace our 64.12 with the letter x. So, and we're going to consider f of x equals x to the 2/3. Now, 64.12. That looks like it's awful close to 64 to me. Now, we're going to, so c equals 64. Now, p is the original. It is the 64.12 itself. But 64 is awful pretty, and we're close to it. 64.12 is not too far away. So we're going to use a tangent line approximation. So now unless you got a calculator to do this by hand, would be quite hard. So note that we got to do f prime of x first. Truth be told, you could go ahead and plug 64 into x to the 2/3 to get your f of c. So for f of c is going to be f of 64. Before I go into f prime, you can go ahead and just do f of 64 right away. Guys, let me do this first, and then we'll find f prime. F of 64, that's 64 to the 2/3. Remember, that's how that's defined. That's the cube root of 64 quantity squared. Okay, but the cube root of 64 is 4, so we're squaring 4. That's just 16. So f of 64, that was fairly easy to find by hand. Okay, not too bad. Now we got to go up and do f prime. Remember, f of x is x to the 2/3. So by the power rule, f prime of x would be 2/3 x to the negative 1/3 power. You remember you bring the 2/3 down, subtract 1 from 2/3, get negative 1/3. Okay, so then we turn around and we go down here and throw 64 into f prime. So that's going to be, so again, now f prime of x is 2/3 x to the negative 1/3, so just throw 64 into x here. So it's 2/3, and put parentheses around the 64 and raise it to the power of negative 1/3. Now you got to, now how do we handle that? Remember, guys, 64 to the negative 1/3 power, that comes downstairs. That can come downstairs with this 3 down here as 64 to the positive 1/3 power. But 64 to the 1/3 power is the cube root of 64. So that goes down there. But the cube root of 64 is also nice. That would just be, well, we've done it up here. Never mind, we've already done it. It's 4. So that's just 4. And so that's just, now, and then 3 times that 4. And that's going to be 12. You can leave a space between a 3 and a radical, but if you get a pure number, put these parentheses around this 4, by the way, okay? Or else put a dot, 3.4 if you don't like these parentheses here. But anyway, 3 times 4 is 12, and 2 over 12 is 1/6. Okay, that wasn't too bad. I won't call it ultra easy, but it was fairly easy. So that wasn't too bad. So now we've got our players. So we've got our actors. They've all came in the building. Now we need to put them on the stage. So f of 64.12 approximately equals f of 64, which we know is 16, plus f prime of 64, which is 1/6, times the difference of 64.12 and 64, which is 0.12, just by pure D arithmetic. Okay, now we can do this by hand. It's not too bad. Guys, by arithmetic, 0.12 divided by 6, well, 6 is going to 12 2 times, so 0.12 divided by 6 would be, well, that'd be 0.02. So this would be 0.02, and 0.02 plus 16 is 16.02. Now, I kind of go through a lot of rigmarole here, but you don't have to go through all this rigmarole. Yeah, 0.12 is 0.12 over 6. You can think of that as, well, what am I doing here? Oops, that shouldn't be 60, should it? That should be 6. My bad, guys. That's 6, not 60. Now, that 600 really is 600. This is a 6, not a 60. And this is 0.12 over 6. Well, that's multiply by 100, multiply 12, but we won't, it'd be nicer to have 12 up here, not 0.12. So multiply by 100 and you get 12. But you got to multiply the 6 by 100 on account of that, and you get 600. But 12 over 600 reduces greatly to 1 over 50, and 1/50th is 0.02. Okay. But really, frankly, if I were you, I wouldn't go through this fractional. If they wanted in fraction form, you could get this you could turn this into an improper fraction as well. But I say forget all that. Decimal is the best way to go here. The whole point of this is to get an approximation to me. I want decimal. 12 divided by 6 is 2, okay? So 0.12 divided by 6 ought to be 0.02, and it is. So there it is. So 0.02 plus 16 is 16.02. Just cut to the chase. Forget this unless your professor just makes you do it. Forget this guy right here, and this guy right here, and even this guy right here, unless your professor just makes you. So I'm going to get rid of those at the risk of losing information. Sometimes less is more, I think. And let me just get rid. There we go. And I'll save that. Just cut to the chase. Okay, but however, if you get your calculator, the actual calculator f of p value is really 16.019999376. Not bad at all. Very close. Now our approximation gave us exactly 16.02. Now the real McCoy is going to be an irrational number. It's never going to stop. It's going to go forever. But hey, you got to admit, for everyday practical purposes, 16.02 is not a bad approximation at all. It's actually wonderful if you ask me. Okay, so my tangent line approximation, my final answer is 16.02. That's my tangent line approximation. Now, your actual calculator value is this big jalopy here. But we're more interested in the 16.02. We're actually more interested in the approximation than we are the exact thing in this situation. Note that dx was 0.12. That's just your p minus c. And note that dy, that's the 0.02. Oops, did I mess it up? I sure did. Oops. So dy is your 0.02. So notice that, so your dy is 0.02, and there's that. And indeed, that's really nice. We're close. Okay, so your dy is this one. That's the 1/6 times 0.12. That's the 0.02. And I'm sorry about that mistake. I'll correct that. I don't want to throw you off guard. So there's that. And if they ask you, this is just if they want the differentials. As far as the tangent line approximation goes, 0.02 or 16.02 is your tangent line approximation, and we're done as far as that goes. But if they want the extra mile, if they want you to give the differentials, here they are, here and here. Okay. But the tangent line approximation is 16.02. Alrighty then. Okay. Now let's see if I got another example rolling here. Consider the square root of 25.22. Now, hey, that's not too far away from the square root of 25. So 25.22 is pretty close to 25 itself. So this is screaming for us to let f of x equal the square root of x, because we're doing a square root function of something. Okay. And now p is the exact 25.22. C is 25, the guy we're close to that's going to behave well. Now, we get f of 25, that's the square root of 25, that's 5 itself. That was nice. Now, guys, if you do f prime, remember, you got to do the derivative first. Remember, f prime of x is 1 over 2 radical x from times past. I'll insert that in there just to remind you. Remember, you do it by the power rule. X to the 1/2 turns into 1/2 x to the neg half. But if you write that in radical mode, that is just 1 over 2 square root x. So we get, recalling that f prime of x equals that. Now guys, now f prime of 25, you got to throw 25 into this guy down here. So f prime of x is this. So throw 25 down here, but that's still not hard to do. Square root of 25 is 5, and then 5 times the 2 that was already down there is 10. So that's 1/10. That still wasn't too hard to do. F of 25 was really easy. F of prime of 25 was pretty easy. So now we've got let's get our actors on the stage to get the thing we're after. F of 25.22 is approximately equal to 5 plus, 1/10. That's f prime. Now, guys, again, we've got to do p minus. We got to multiply that 1/10 by the difference of 25.22 and 25. 25.22 minus the 25, these two subtracted, or p minus c that is 0.22. Now, lest there be any mistake, p minus c can be negative sometimes. It is p in front. It is p minus c in that order. So, and you can get a negative number sometimes. We don't get it in this problem, but there are situations if p is smaller than c, yeah, you'll get a negative number right here. That just means your actual answer or your approximation will be below your actual answer instead of above it. It's no big deal. But anyway, so you get 0.22 because if you subtract these two, you just get 0.22. So there's that. And then you do PEMDAS. By PEMDAS, you got to multiply 0.22, or, well, by 1/10, which is the same thing as 0.22 divided by 10. That's just 0.022. And 0.022 plus 5 is 5.022. So there's that. And I really should say 0 instead of O. I'm just a creature of habit. So 0.22 divided by 10 is 0.022, and then take 0.022, which is your dy, by the way. That's dy. And add that to 5, and you get your tangent line approximation, which is 5.022. And hence, our tangent line approximation is hence 5.022. Now, your professor, and if they want the differentials, dy will naturally be 0.022, and dx will be 0.22, okay? But that's just if your professor asks for the differentials. I'm sure he or she will ask for the tangent line approximation. Some professors call this the just the linear approximation, whatever. Now, the actual value is, now, you can't get this actual value without the calculator. It would take you a long time to do it by hand. Actually, you never would get done. It's irrational. But this is just, it's roughly this. It actually goes on forever. It doesn't even pattern. It doesn't repeat in any pattern. It just goes forever with no real pattern. That's what an irrational number does. There's no real pattern, yet it goes forever anyway. But you get this, and no, that's not bad. 5.0219, that's pretty close to 5.022. So we got a handsome, very nice tangent line approximation here. And if your professor wants the differentials, dx is 0.22, whereas dy is 0.022.